Hey there, today's topic is on dual nature of matter. This is a topic that tells us that everything around us, including our own bodies, might secretly behave like wave because according to quantum physics, matter does not just exist like particle, but it also exists like waves. So what is the basis of this assumption? How do we come up with that? So that's what today's lesson is about. This is part of your A-level physics, so let's get going. So particle nature of EM radiations. Now, we have done photoelectric effect in the previous videos, so we kind of know that EM radiations, which were initially supposed to be behaving like a wave, was then proven by Einstein that these waves are made up of small particles of energies. So the particles of energies, so they are kind of made up of small packets of energy, and these packets of energy are known as photons. So that was the explanation of photoelectric effect given by Einstein, for which he even got a Nobel Prize. Now, fine, so wave was our normal light EM radiations were proven to have wave particle nature. But then if waves are behaving like particle and nature loves symmetry, so Louis de Broglie was a physicist. He came up with a hypothesis. Remember, it's still a hypothesis. He came up with a hypothesis that if photons are particles of light, they behave like wave. Okay, so obviously then the particles of matter like electrons or protons should also behave like waves. So particles, so if I'm writing the word particles, that means it's the particles of matter, electrons, protons, all of that. So particles should also behave like wave. So this was his hypothesis. He published this in his PhD thesis. Should also behave like wave. So that was the assumption here. Okay, like waves. So this was his hypothesis. And if the particles are behaving like waves, say according to Einstein, the wavelength of these photons was h over p. So the momentum of these particles, because if the photons are particles, they should have a momentum. So the momentum of these photons were calculated using this equation. H is a Planck's constant. So the particles should also behave like waves. And what would be the wavelength? The wavelength of these particles would also be given by this. P is a momentum, and P can be calculated using mass times velocity. H is Planck's constant. Now this was still a hypothesis till Davison and Germer, so these were the two physicists who were doing an experiment to study the surface of nickel, but accidentally ended up seeing along this detector, they ended up seeing something like this, an intensity of unusual and unrelated peaks. So this was a peak of intensity which was observed on the screen here. They were not expecting the intensity to vary like this. Now this was, so let me just explain it. So this is the kind of rings, the diffraction rings that we obtained in the waves, X-rays. They ended up getting the same kind of pattern on the screen here. So then, because it was a diffraction pattern, unrelated, unexpected peaks. So then they ended up discovering accidentally that electrons have a wave nature. So because they have a knack of detail, they were observing the results with a detail. They were good physicists, good scientists. So they discovered that electrons were actually behaving like wave. Why? Because they were exhibiting the diffraction pattern. Now, how was then that experiment done? So it was done in a vacuum tube so that there was no interference, kind of, so something like this. So it was a strong piece of metal which was heated to emit electrons, and then it was given some high voltage to accelerate it. Okay, so let's say here it has high voltage and the electrons are still behaving like particles, and then they were allowed to pass through a crystal, maybe a graphite crystal. Okay, so very thin graphite screen, and then after passing through this, the electrons now started behaving like wave, because on a screen here a diffraction pattern was observed. So here the diffraction pattern was observed. So it was should have gone straight if it was particle, but instead there was a diffraction pattern here with central maxima and continuous distribution of energy around it. So this was here some kind of anode. Anode means it was there to give positive voltage. So when you give positive voltage to electron, they get a kinetic energy, and kinetic energy of those photons is EV, because it's in electron volts. And how do you convert electron volts to joules? You have that in your equation sheet or data sheet. Just plug in the value of electron, which is 1.6 times 10 to the power minus 19 joules. So if I give it 10 volts, the kinetic energy would be 10 electron volts. If I give it 100 volts, the kinetic energy would be 100 electron volts. This is a piece of metal which is emitting electrons on heating. So this is called thermo-ionic emission, because you're emitting electrons by heating it. So thermo-ionic emission, electrons are behaving like particles and then passing through the graphite, which is acting like diffraction grating, very thin slits, and the electron then, when it comes out, it is behaving like waves. Now what you need to know that how the energy of the electron depends on the voltage, as you can see from here, is directly proportional to anode voltage. So larger the anode voltage, larger would be the energy of these electrons. So if we don't want the electrons to penetrate too much deeply into the graphite crystal, we'll give them less energy. So this is the kind of thing happening here. So electrons, and then when they hit the atomic spacing of the graphite, because of atomic spacing is acting like now diffraction grating, and the electron gets diffracted as waves. So a high intensity at the central maxima, and then the intensity is decreasing. That's what's happening. So this graph here is showing the intensity peaking at the central maxima, and as you go away from the central part, it has less intensity, but intensity is still there. That means electron is bending and going somewhere else. So bending happens only with the waves. Particles don't bend. So this was the first thing that we need to know, that the energy of the electrons depends on the anode voltage. Now, how would the wavelength depend on energy? So sorry about that. So if now you we try and find out the relation between accelerating voltage and wavelength. Now we know that wavelength is h over mv, where mv is the momentum, and we also know that you can write energy, relation between energy and momentum would be, so if I write P equals to mv and kinetic energy is half mv square, you have this equation in your data sheet. So P square over 2m. So I can just rearrange this. So I write 2me is P. So I'm just writing here. So wavelength is h over 2me. Now E is the kinetic energy which is coming because of the voltage that you're giving at anode. Higher voltage is higher acceleration. So I'm just writing it as 2mev. That's the equation. So as you can see, what would happen if capital V, which is voltage, is increased? If voltage increases, the wavelength would then decrease. So because the wavelength is decreasing, the diffraction angle becomes smaller. That is, the rings would become tighter. Say decreases. Okay. And if obviously the voltage would decrease, the wavelength would increase. Now this is if you are doing a diffraction experiment with low energy and the electrons have a very low energy, then they will just go to the surface and they'll give this kind of pattern. So this pattern is with polycrystalline graphite and this one is with pure tungsten. So, and at a energy of 138 electron volts. So kind of, so as you can see, this one looks like the rings, the diffraction rings. So if I want my electron to give me a pattern for polycrystalline graphite, then the wavelength of the electron should be order of the atomic spacing. So my wavelength of electron should be nearly equal to atomic spacing. If it is not, my electron will not be diffracted, just similar to the waves. So for waves to be diffracted, the wavelength should be order of the slit separation. So similarly here the slits, if I have a graphite crystal here, then the atomic spacing of the graphite, they are acting like grating. So if my wavelength is not of the order of this width, it cannot be diffracted. So the lambda or wavelength of electron should be of the order of atomic spacing, so which is, let's say, around 10 to the power minus 10 meters. So if I then use this equation, that my wavelength is 10 to the power minus 10 meters, and I rearrange this equation to get V, so lambda squared equals h square over 2mev, and then rearrange to get capital V as h square over 2me lambda square. So if you plug in the value of lambda as 10 to the power minus 10, E is the charge of electron, m is the mass of electron, everything is there in your data sheet, h is Planck's constant. So if you plug in all the values, the voltage that is coming around is of the order of 150 volts. So if you accelerate electrons by around 150 volts, it can then be diffracted by the crystalline graphite, and then you would see the diffraction pattern. Okay, so we have done this already, electron speed and diffraction. So speed means kinetic energy, and kinetic energy, where is the kinetic energy of electron coming from? Anode voltage. So the larger voltage is larger kinetic energy and hence the larger speed. And if the speed is higher, momentum is higher too, increases with speed. and if momentum is increasing, the wavelength, which is h over p, which is momentum, p increases, this decreases. So wavelength has now decreased, so the diffraction pattern will become less, it will be smaller, it will be tighter, so you'll have less rings on the screen. Now, uses of electron diffraction. It is used to study atomic spacing, defects in metals. Okay, in simple words, electron diffraction is used to see what ordinary light cannot. If I want to see what defects are there in a piece of metal, I can't see if I do not have electron diffraction happening. So it is used to study defects of atomic arrangement in metals. It is used in nanotechnology, electron microscope, the biggest example. Now, let's do then the next slide. Here you go. Let's do this one. Electrons are accelerated through a larger potential difference before striking a crystal lattice. What happens to their diffraction pattern? So if you are accelerating through a larger potential, what have you done? Larger voltage means, go ahead, pause and try to do it. Sorry. Try to do it yourself. So larger kinetic energy. Larger kinetic energy would mean larger momentum, which would then mean less wavelength. So this is the answer then. Electron diffraction provides evidence that electrons exhibit wave-like properties. Next, in an electron diffraction experiment, diffraction occurs only when? When does the diffraction occurs? Obviously, any kind of diffraction will always occur when wavelength is comparable to the spacing. Okay, let's do this question. Again, pause and try to do it yourself. Everything is given in the question. Try and use the equation to calculate momentum and then the wavelength. Okay, de Broglie's wavelength is lambda equals to h over momentum. Okay, go ahead and do it. So the value of h is just writing here for your help 6.6 10 to the power minus 34 joules second, and let's just take it up to 2 decimal points, 6.62, 6.63. Okay, and then once you've done, check your answer. That's your answers. Next, pause and do it, and then once you've done, check your answer. Okay, so this is all the statements you should have written. And then the last one, if your student is increasing the accelerating voltage in an electron diffraction experiment, describe and explain how the pattern changes. Now just pause and try to write the answer yourself. Once you've done that, check. All right, so that's about electron diffraction, kind of the basis of the quantum physics. So that's all for today. Keep revising. Thank you so much.